After talking about the subgrade, let's look at the unbound granular materials. There are two methods to measure the modulus of the unbound granular materials: the direct measurement method and the presumptive values method. In direct measurement method, the modulus is measured in a triaxial cell and repetitive loading conditions. Normally, the modulus of elasticity is the stress divided by strain or slowly applied load. The resilient modulus is stress divided by strain or rapidly applied loads, like those experienced by pavement. So in this stress strain curve, the recoverable part of the actual deformation response, in other words, the gradient of the recoverable stress strain curve is the resilient modulus, MR. The second method, or the presumptive value method, is to refer to empirical tables. This table includes values for base quality materials, high standard crushed rock, and normal standard crushed rock, and base quality gravel, and sub-base quality materials. Normal standard crushed rocks are those commonly used by road authorities. Because the moduli of unbound granular materials are stress dependent and dependent on moisture and compaction levels in the road bed, caution must be exercised in applying this empirical data. This table may be used as a guide when assigning maximum value to granular materials and seeing bituminous surfacings when other more reliable information is unreliable. The unbound granular materials are the anisotropic materials, and the anisotropy is the ratio of vertical modulus and horizontal modulus, which is 2. So if you know the vertical modulus of the unbound granular materials, you can easily work out the corresponding horizontal modulus. The presumptive vertical modulus of top sublayer of normal standard base material under asphalt surfacing or cemented material can be seen from this table. This table 6.4 and 6.5 in the next slide could be used as a guide when assigning maximum vertical modulus value to base quality crushed rock materials and asphalt surfacings when other more reliable information is available. The first column in the table is the thickness of overlying bond material, and second row is the modulus of overlying bond material. If the thickness of the overlying bond material is 75 millimeter and the modulus of overlying bond material is 2000 megapascal, then the vertical modulus of top sublayer of normal standard base material is 350 megapascal. Normally, the maximum moduli used for subbase should not exceed that for normal standard base as indicated in this table. As you can see here, how the modulus reduces. So they reduces with the depth, with the increase of the depth, because the stress is varying with depth. So this is a workaround for use in our linear elastic model to overcome the deficiencies of not allowing for the stress dependency of individual layers in terms of the granular modulus. This table contains the suggested vertical modulus of top sublayer of high standard base material. If we know the thickness of the overlying bond material, for example, 100 millimeter, and modulus of overlying bond material. For example, 3000 megapascal. And then the vertical modulus of top sublayer of high standard base material is 410 megapascal. Now let's go back to look at the previous example. According to previous formula, equation 21, the EV is calculated as 696 megapascal, while assuming high standard crushed rock as granular material with 40 millimeter overlying bond material, and referring to table 6.5. This table is 40, and no matter the modulus of the overlying bond materials, we can see the vertical modulus of top sublayer of high standard base material. They are all 500 megapascal. So that's how we pick up the value here. So the EV for this unbound granular material is the minimum of those two values. So it is 400 megapascal. Another important pavement material is cement, which is considered to be isotropic with tensile strength. In the normal operating condition of the pavement, its elastic response is normally regarded as linear with an elastic modulus and Poisson's ratio. The Poisson's ratio is shown to have relatively little influence on pavement thickness requirements within the normal range. Commonly, it is assumed to be 0.2. There are mainly two methods to determine the design modulus of cement: the laboratory tests and empirical values in the design table. The laboratory test includes the flexural test, direct tension test, longitudinal vibration test, indirect tensile test, and direct compression test. The setup of the 3-point flexural loading test is shown here in the bottom figure. The sample is supported by two supporting pins, and there's a loading pin to apply the force. This 3-point loading of sample with a span over depth ratio greater than 3 is favored for modulus characterization, as the test conditions are considered to simulate the strain gradients generated within a pavement layer. The presumptive values of elastic characterization of cemented materials, including design modulus, could be found from table 6.7. The modulus values presented in this table may be used as a guide if no other more reliable information is available. The moduli of cemented materials are dependent on a number of factors, such as the material quality, the binder content, and density. The presumptive values can't account for variations in these important parameters, so it should be treated with caution. Previously, we have covered the pavement materials from bottom to top, including the subgrade, unbound granular materials, and cemented materials. The last important pavement material is asphalt. The resilient modulus of the asphalt could be measured using the standard indirect tensile test IGT, adjusted to the weighted mean annual pavement temperature WMAPT and the rate of loading in the roadbed. This is because the asphalt modulus is sensitive to temperature and rate of loading. The higher the temperature, the lower the modulus. The higher the loading rate, the higher the modulus. So the temperature environment of asphalt must be taken into account in pavement design and analysis. Table 6.413 presents modulus values from indirect control test and the standard test conditions for typical dense gradient asphalt mix used by Australia's member authorities. The results are for laboratory manufactured samples with the likely range of values together with typical recommended values. These values are provided for a range of mix size and binder type. For example, for binder class C320 and mix size of 14, the typical modulus of dense gradient asphalt is 5,000 megapascal. The second method is estimating the modulus from the bitumen properties and mix volumetrics using shell normal graph in combination with the in-service temperature WM APT and rate of loading in the roadbed. This method is developed by Shell to obtain reasonable estimates of modulus of mix, which include conventional bituminous binders. The Shell method has two stages. Firstly, the modulus of bituminous binder is determined for specific bitumen in the specific pavement design situation. For example, the traffic road, traffic speed, and operating temperature. Then asphalt modulus is determined from the bitumen modulus and the volumetric composition of the mix. Now let's look at one example. The normal graphs produced by Shell to undertake these above two steps are reproduced as figure 6.9 and figure 6.10. In determining the asphalt design modulus, you need to consider what your in-service temperature would be for your project and also your rate of loading. The time of loading is 1 divided by V, where this V that's with the unit of kilometer per hour is the design heavy vehicle speed. The operating temperature is equal to the effective temperature of asphalt WM APT, and T800 PEN is the temperature at which the penetration of bitumen is 800 or 0.1 millimeter. Finally, the PI is the penetration in index of bitumen measuring temperature susceptibility. So for this example, the operating conditions are temperature equal to 27 degrees, and loading time is 0.02 seconds. T800 PN is 58 degrees, and PI is negative 0.5. So firstly, we need to connect 0.02 seconds on the time scale with temperature difference 58 minus 27 equal to 31 degrees. So we read 31 here and connect 0.02 to 31. And then we extend the dashed line to intersect with the lines of stiffness modulus with PI of negative 0.5. So it's here, negative 0.5 here. Then we read from the value in the horizontal axis. We can see that the stiffness of the bitumen determined from this normal graph is SB equal to 20 megapascal. So that's the first step. After we get the stiff modulus of the bituminous binder, for this case is 20 megapascal. Next, we go to the figure 6.10. So we label SB here, 20 here. So, and if we know the effective volume of binder, which is VB equal to 11%, and also the volume of mineral aggregate, VG, that's 82%, we can refer to the figure 6.10. So we just draw a horizontal line through this 20 and find the VB equal to 11% roughly here. Then we just draw a vertical line and intersect with VR, the line with VG of 82%. So 80 is here, 85 here. So 82 somewhere in between, or roughly in the middle. And then we just draw the final horizontal line intersect with the vertical axis. And if we take the reading, so we can find the stiffness modulus of the bituminous mix is roughly 3000 megapascal. You have learned the right diagram from our last lecture and corresponding mathematical expressions and physical meaning of each parameter. So in this example, we have used the VB and VG here. So I won't just go into more details for now, but just I put it here for your reference. A summary of this lecture: we have briefly reviewed the multi-layered structure of flexible and rigid pavement and their differences. The factors influencing the material performance, including the project reliability, the construction and maintenance, and the environment, are discussed. We also learned the damage models for asphalt, the cemented materials, and subgrade. The measured and presumptive properties for subgrade and pavement materials are discussed. We also learned the sublayering of unbound granular materials and the calculation of the vertical modulus. Finally, the shell method for determining asphalt modulus is discussed and practiced. That's all I have for this lecture, and I appreciate your attention. In next lecture, we will continue to learn the structural design of flexible pavement. Thank you and have a great day.